Have you ever wondered what it would feel like to float above the world and see everything at once? To watch the sun rise 16 times in a single day, to see entire continents pass beneath you in moments, to witness the delicate blue line that separates life from the cosmic void? What if I told you that from 400 kilometers up, all the things that divide us, borders, conflicts, differences, simply vanish, and you can finally see Earth for what it truly is, a singular, magnificent home spinning through the darkness? Join me on a journey to the most beautiful view in the universe, and let's discover together what our planet looks like when we finally step back far enough to see the whole picture. This is Earth as it appears from the International Space Station, orbiting at precisely 400 kilometers above the surface you're sitting on right now. Up here, traveling at 17,500 miles per hour, the station completes one full orbit every 90 minutes, offering an endless panorama of our planetary home. What strikes you first isn't the land or the features you might expect, it's the overwhelming blueness of it all. Oceans cover 71% of Earth's surface, creating that signature blue marble appearance that has captivated humanity since we first glimpsed it from space. The sight is more than beautiful. It's a revelation that changes how you understand everything you've ever known about home. From this altitude, your perspective shifts in ways difficult to describe to those who haven't experienced it. The horizon stretches 2,300 kilometers in every direction, far enough to see weather systems spanning entire regions, to watch storms being born and dissipate, to observe the intricate dance of clouds and ocean currents. You begin to notice patterns invisible from the ground, the way trade winds shape cloud formations into repeating ribbons across the Pacific, how ocean colors shift from deep navy to brilliant turquoise over shallow banks and coral reefs. This isn't just sightseeing, it's witnessing the living, breathing systems that regulate our planet's climate, produce our oxygen, and make life itself possible in this corner of the cosmos. Let's drift over to where ocean meets land, where the story becomes even more complex and beautiful. See how the water changes color as it approaches the continental shelf? That brilliant turquoise isn't just aesthetically pleasing, it's telling you about depth, about sediment, about the shallow zones where sunlight penetrates all the way to the seafloor and life flourishes in extraordinary abundance. The Bahamas appear as swirls of aquamarine and sapphire against deeper blue, each shade revealing underwater topography as clearly as if the ocean were transparent. Along coastlines, you can trace river mouths by their sediment plumes, brown ribbons extending far into the sea, carrying nutrients from continents to feed marine ecosystems thousands of kilometers away. Now we're approaching South America, and you can see one of Earth's mightiest rivers meeting the Atlantic Ocean. The Amazon discharges more water than any other river on the planet, enough to fill over 200 Olympic swimming pools every single second. From up here, you watch that fresh water laden with sediment from the Andes Mountains and the rainforest create a massive brown plume that extends hundreds of kilometers into the blue ocean. This isn't just water flowing, it's the lifeblood of a continent, carrying nutrients, minerals, and organic matter that will feed marine life across a vast swath of the Atlantic. The interface between brown river water and blue ocean water creates swirling patterns, visible proof of the turbulent mixing where two worlds collide. As we continue our orbit, something remarkable happens. You begin to see Earth not as a collection of separate places, but as an integrated whole. The ocean currents you're watching don't stop at borders. The clouds forming over the Atlantic will bring rain to Europe. The dust rising from the Sahara will fertilize the Amazon rainforest. Everything connects to everything else in an intricate web of relationships that sustains the entire planet. This realization, simple yet profound, is what astronauts describe as the overview effect. Borders that seem so permanent and important from the ground simply don't exist up here. There are no lines dividing nations, no walls separating peoples, just one beautiful, fragile sphere of life floating in an infinite darkness. Every 90 minutes this view repeats, yet it's never quite the same. Cloud patterns shift, sunlight angles change, different parts of the planet rotate into view. Astronauts aboard the ISS have photographed Earth over 3.5 million times since operations began, yet they report never tiring of the view. Ooh. Each pass reveals new wonders, perhaps a volcanic eruption sending ash high into the stratosphere, maybe a tropical cyclone organizing itself into that characteristic spiral shape, or simply the way sunlight glitters off ocean waves in a phenomenon called sunglint, creating a brilliant silver path across the water. These aren't static images. You're watching a living planet in constant motion, constantly changing, yet somehow maintaining the delicate balance that makes it hospitable to life. This perspective fundamentally changes what it means to be human. Up here, the atmosphere that you've breathed your entire life, that seems infinite when you're standing on the ground, reveals itself as impossibly thin, a delicate veil separating life from the vacuum of space. The conflicts that dominate news cycles appear small and temporary when viewed against the backdrop of cosmic time. The environmental challenges we face become visceral and urgent when you can literally see the planet changing before your eyes. But there's also profound hope in this view, because you realize that we truly do share one planet, one atmosphere, one future. What happens in one place ultimately affects everywhere else. This isn't abstract philosophy. It's observable, measurable reality, visible from 400 kilometers up. As we complete this first orbit together, take a moment to simply breathe and absorb what you're seeing. This isn't science fiction or fantasy. This is your home, your planet, the only world in the entire known universe confirmed to harbor life. Every person you've ever known, every story ever told, every triumph and tragedy in human history happened down there on that blue and white sphere. From up here, all of it seems both infinitely precious and surprisingly small, a reminder that our time on this planet is brief and our responsibility to protect it is profound. Let this view settle into your consciousness as we continue our journey, exploring the specific features and systems that make Earth not just beautiful, but uniquely alive. As the sun rises ahead of us on this orbit, something extraordinary becomes visible. The atmosphere itself. When photographed edge-on during sunrise or sunset, Earth's protective envelope reveals distinct colored bands that correspond to different atmospheric layers. The deepest band appears orange and red. That's the troposphere, the densest layer where all weather occurs, where you're sitting right now, where 80% of the atmosphere's total mass resides. Above it, a pink and white band marks the stratosphere, home to the ozone layer that shields life from harmful ultraviolet radiation. Higher still, a light blue layer shows the mesosphere, where temperatures plunge to -85 degrees Celsius and meteors burn up in brilliant streaks. Finally, a dark blue fading to black marks the thermosphere, where we orbit and where auroras dance in ethereal curtains of light. Here's something that will change how you think about breathing. If Earth were the size of an apple, the breathable atmosphere would be thinner than the apple's skin. Let that sink in for a moment. This entire life-supporting envelope, every breath ever taken by every creature that ever lived, exists in a layer so thin it's almost impossible to comprehend. Earth's diameter measures 12,760 kilometers, while 99% of atmospheric mass lies within just 31 kilometers of the surface. That's a ratio of roughly 1 to 400. When you fly in a commercial aircraft at 11 kilometers altitude, you're already above 77.5% of the atmosphere. Everything you need to survive, oxygen, protection from radiation, stable temperatures, exists in this impossibly delicate shell. Astronaut Frank DeWinnie described it perfectly. This thin blue line makes our planet livable. He's absolutely right, yet what he didn't say explicitly is just how fragile that blue line truly is. From orbit, you can see the atmosphere doing its work in real time. Watch how clouds form, how weather systems develop, how invisible air currents shape visible patterns in the cloud cover. Those beautiful spiral cloud formations aren't random. They're revealing the Coriolis effect, the rotation of the planet influencing the motion of air masses. The clear blue sky you take for granted is the result of molecules scattering sunlight, a phenomenon that would be impossible without this specific mixture of gases at this specific pressure. Everything about this atmosphere represents a delicate balance evolved over billions of years. The composition of this precious air envelope tells a story of both stability and change. Nitrogen makes up 78.08%. Oxygen comprises 20.95%. These proportions have remained relatively stable for millions of years. But carbon dioxide, though present in much smaller amounts, tells a different story entirely. Since systematic measurements began at Mauna Loa Observatory in 1958, atmospheric CO2 has risen from 315 parts per million to over 424 parts per million today. In May 2025, levels are projected to reach 429.6 parts per million. This increase represents a rate of change 100 times faster than natural cycles like ice age transitions. Half of the total atmospheric CO2 increase since 1750 has occurred just since 1980. You might wonder, can we actually see these atmospheric changes from space? The answer is both yes and no. The carbon dioxide itself is invisible, but its effects are not. Satellites track melting ice sheets in Greenland and Antarctica, measure rising sea levels millimeter by millimeter, monitor vegetation patterns shifting toward the poles as temperatures climb, and observe coral reefs bleaching when ocean temperatures exceed their tolerance. During 2024 alone, confirmed as the warmest year in instrumental records, global temperature reached 1.6 degrees Celsius above pre-industrial levels. From orbit, you can watch these changes unfold. Arctic sea ice declining at 12.4% per decade, the last 18 years representing the 18 lowest extents in the 45-year satellite record. The atmosphere appears pristine and eternal, yet the data reveals a system under unprecedented stress. But the atmosphere isn't just changing, it's also performing daily miracles. Watch as the sun rises over the planet's limb, illuminating the atmospheric layers in sequence. First, the upper atmosphere catches the light, creating that brilliant blue glow. Then, layer by layer, sunlight penetrates deeper until finally it reaches the surface, bringing day to another part of the world. This happens 16 times during each 24-hour period for us up here on the ISS, creating a rhythm entirely different from the single sunrise and sunset you experience on the ground. Each one is unique, each one beautiful, and each one a reminder that this thin envelope of gas is what makes such beauty possible. Without atmosphere, there would be no sunrises, no blue sky, no red sunsets. Just the harsh transition from blinding sunlight to absolute darkness. The atmosphere also produces phenomena that seem almost magical when viewed from above. During periods of high solar activity, such as the solar maximum reached in mid-2024, the atmosphere puts on one of nature's most spectacular displays, the aurora. We'll explore these dancing lights in detail later, but for now, simply observe how they appear from our vantage point. Shimmering curtains of green, red, and purple light extending from 80 to 500 kilometers above the surface, visible from unusual latitudes during strong geomagnetic storms. These aren't just beautiful, they're visible proof of invisible processes. Charged particles from the sun, guided by Earth's magnetic field, colliding with atmospheric gases and releasing energy as light. Your protective atmosphere is literally glowing. As we leave this section of our journey, consider the miracle you're witnessing. This thin blue line, barely thicker than a sheet of paper when scaled to the size of a globe you can hold, contains all the air ever breathed by all life on Earth. It's the reason water exists as liquid on our surface, the shield that protects us from deadly radiation, the blanket that keeps temperatures within the narrow range where life can thrive. Yet for all its importance, it's also terribly fragile, vulnerable to changes in composition, sensitive to disruptions, finite in its capacity to absorb our impacts. The astronauts who have floated where we are now often report the same realization. Seeing how thin the atmosphere truly is makes you understand, in a visceral way that no intellectual knowledge can match, just how precious and precarious our existence really is. Let's descend our gaze now to what dominates Earth's appearance from space. The oceans. Covering 71% of our planet's surface, water is the defining feature of Earth, the substance that makes life as we know it possible, and the primary reason our planet appears blue from the cosmic perspective. But from orbit, you quickly learn that the ocean isn't a single uniform entity. It's a complex, ever-changing system of currents, temperatures, colors, and biological activity. Look closely at the Pacific, and you'll see variations in blue shading from nearly black in the deepest trenches to brilliant turquoise over shallow seamounts. Each shade tells a story about depth, sediment load, phytoplankton concentration, and temperature. The ocean from space becomes a readable text if you learn its language. One of the most mesmerizing features visible from orbit is phytoplankton blooms, vast aggregations of microscopic organisms that color the ocean in swirls of green, brown, or even milky turquoise. These aren't accidents of chemistry. They're the foundation of ocean food webs, the organisms that produce roughly half of Earth's oxygen, the creatures that draw down carbon from the atmosphere and help regulate our planet's climate. Some blooms stretch for hundreds of kilometers, visible as emerald spirals and eddies that trace invisible ocean currents. Scientists using satellite data from 760,000 MODIS images have documented that coastal phytoplankton blooms are expanding and intensifying, starting 1 to 2 weeks earlier in the 21st century than in previous decades. These changes ripple through entire ecosystems, affecting fish populations, marine mammals, and ultimately the humans who depend on ocean productivity. Ocean currents themselves become visible from space through temperature contrasts and color differences. The Gulf Stream appears as a ribbon of warm orange-red water against cooler blue surroundings when viewed in infrared satellite imagery, typically 100 kilometers wide, 800 to 1200 meters deep, moving at surface speeds reaching 2.5 meters per second. This massive river within the ocean transports more water than all of Earth's rivers combined, carrying warm tropical water northward and moderating European temperatures by up to 9 degrees Celsius compared to equivalent latitudes in North America. Without the Gulf Stream, London would have a climate more like Labrador, Canada. From orbit, you can trace this current's path across the entire North Atlantic, watching it deliver heat energy from the tropics to higher latitudes, driving weather patterns and sustaining ecosystems thousands of kilometers from its origin. The Antarctic Circumpolar Current, though less famous than the Gulf Stream, is actually Earth's largest current system, and from our polar orbit, we get perfect views of the Southern Ocean. This current circumnavigates the entire planet, transporting 137 million cubic meters of water per second while connecting the Atlantic, Pacific, and Indian Oceans. It's the ocean's great mixer, stirring nutrients and heat around the globe, maintaining the temperature gradients that drive global ocean circulation. Recent studies suggest this current is speeding up due to increased temperature gradients, with potential 20% strength loss by 2050 carrying widespread implications for ocean circulation and climate. From above, the Southern Ocean appears deceptively calm, its blue-gray waters seemingly peaceful, yet those waters are actually racing around Antarctica at speeds that make this the most dynamic ocean region on Earth. As we continue orbiting, we pass over regions where the ocean reveals human impact in ways both subtle and dramatic. In some areas, you can see the effects of warming ocean temperatures. Coral reefs that once appeared vibrant blue and green now show pale, bleached colors indicating stress or death. Ocean heat content in the upper 2,000 meters reached its highest level ever recorded in 2024, with the increase equaling 140 times the world's total electricity generation in 2023. This heat doesn't just sit there. It intensifies storms, disrupts marine ecosystems, and contributes to sea level rise through thermal expansion. From space, the ocean's beauty remains breathtaking, but the subtle changes in color, temperature, and biology tell a story of a system under unprecedented stress from human activities. Yet the oceans also demonstrate remarkable resilience and complexity that gives reason for hope. Watch as atmospheric rivers, narrow bands of intense moisture transport, deliver life, giving water from ocean to land. These features carry water vapor equivalent to 7 to 15 times the flow of the Mississippi River at its mouth, yet they occupy less than 10% of any given extratropical latitude. They're invisible to the naked eye from space, but their effects are dramatic, bringing rain to drought-stricken regions, filling reservoirs, nourishing forests and farmlands. The oceans act as Earth's primary climate regulator, absorbing 33% of human carbon dioxide emissions, storing vast amounts of heat, and driving the atmospheric circulation that distributes moisture around the planet. This isn't a passive system, it's an active participant in maintaining planetary habitability. The ocean's daily transformations add another layer of wonder to the view from space. During daylight passes, sun glint creates brilliant silver paths across the water's surface where the angle of reflection is just right, a dazzling mirror effect that can extend for hundreds of kilometers. At night, the ocean becomes a dark canvas against which lights from fishing boats create constellations, marking squid fishing fleets off Japan or Argentina with thousands of bright points that rival the stars above. Bioluminescent plankton, though too subtle to see from orbit, occasionally create glowing trails behind ships visible in long exposure photographs. The ocean is never static, never the same twice, always revealing new patterns and phenomena to those patient enough to watch. As we prepare to shift our focus from water to land, take a moment to appreciate what these oceans represent. Every drop of water on Earth today fell as rain billions of years ago, cycled through clouds and rivers and seas countless times, supported life in forms too numerous to count, and continues its endless journey through the water cycle. The oceans you're looking at contain roughly 1.3 billion cubic kilometers of water, enough to cover the entire planet 300 meters deep if the seafloor were flat. This water moderates temperatures, drives weather, supports food webs, and makes Earth unique in our solar system. From space, the oceans aren't just pretty blue surfaces, they're the circulatory system of a living planet, and understanding them is essential to understanding life itself. Now let's turn our attention to the 29% of Earth's surface not covered by water, the continents, islands, ice sheets, and deserts that create the incredible diversity of landscapes visible from orbit. From up here, landforms reveal their true structure and scale in ways impossible to appreciate from the ground. Mountain ranges appear as wrinkled, textured bands stretching for thousands of kilometers. The Himalayas look like a crumpled blanket of white peaks. The spine of South America shows the Andes running from Colombia to Chile, and Africa's Great Rift Valley traces a path that will eventually split the continent in two. These aren't static features, but rather ongoing geological processes, the visible evidence of tectonic plates colliding, separating, and grinding past each other at speeds measured in centimeters per year, yet producing landforms of incomprehensible majesty. Deserts present a different kind of beauty from space. Vast expanses of tan, orange, and red that seem almost abstract in their patterns. The Sahara Desert, visible in its entirety from certain orbital positions, stretches 9 million square kilometers across North Africa, roughly the size of the entire United States. From above, you can see the transition zones, green forests of Guinea-Bissau giving way to the semi-arid brown Sahel, which then fades into the vegetation, less expanse of pure sand and rock. The desert isn't uniform. Vast sand seas create rippling patterns like frozen ocean waves, rocky plateaus show ancient geological formations, and occasional oases appear as brilliant green dots against endless tan. This view reveals something profound: how climate zones organize themselves in bands across the planet, how precipitation patterns create these dramatic transitions from lush to barren in just a few hundred kilometers. Vegetation patterns visible from space tell stories of seasons, climate, and ecological health. During Northern Hemisphere spring, you can literally watch the green wave move northward as trees leaf out and grasslands awaken from winter dormancy. Satellite vegetation indices, measurements of green reflectance from plants, show dramatic changes over 16-day periods as continents transform from winter brown to spring green. The Amazon rainforest appears as a deep, dark green even in dry season, maintaining its photosynthetic activity year-round and drawing down approximately 2 parts per million of atmospheric carbon dioxide during the growing season. In autumn, the process reverses, with green fading back toward brown as leaves fall and plants enter dormancy, releasing that carbon back into the atmosphere in an annual breathing cycle superimposed on long-term climate trends. Ice sheets and glaciers create some of the most striking features visible from orbit. Antarctica appears as a brilliant white continent roughly the size of the United States and Mexico combined, covered by an ice sheet averaging over 2 kilometers thick. From space, you can see the ice shelves extending into the ocean, the mountain ranges poking through the ice, and the subtle blue tint of compressed glacial ice that's thousands of years old. Greenland shows similar features on a smaller scale, a vast white dome fringed by dark, rocky coastline. But satellite measurements reveal changes invisible to casual observation. Antarctic sea ice hit its second lowest winter maximum in satellite history during 2024 at 17.16 million square kilometers, and summer minimums have consistently ranked among the lowest on record since 2017. The ice isn't just beautiful, it's a critical component of Earth's climate system, and it's changing. Rivers, when viewed from space, reveal the fundamental connection between atmosphere, land, and ocean. They appear as dark blue or brown ribbons threading through landscapes, sometimes straight for short distances, but ultimately following curved, meandering paths dictated by topography and geology. The Nile River, clearly visible across Egypt's desert, has sustained civilizations for thousands of years, creating a narrow ribbon of green life through an otherwise barren landscape. The Mississippi River system drains 41% of the continental United States, visible from orbit as an intricate network of tributaries converging toward the Gulf of Mexico. These aren't just geographic features, they're the arteries of continents transporting water, sediment, nutrients, and life from mountains to oceans, shaping landscapes and supporting ecosystems along their entire length. Human impact on land surfaces becomes undeniable from space. Agricultural areas appear as geometric patterns, the circular irrigation fields of the American Great Plains creating perfect green circles against brown backgrounds, the rectangular rice paddies of Southeast Asia forming intricate mosaics, the plantation monocultures creating uniform blocks of single colors. Urban areas show as gray or tan patches, their street grids creating geometric patterns distinct from any natural formation. At night, these cities light up like constellations, their glow visible from 400 kilometers away. Deforestation appears as brown patches expanding into green forests. The Amazon particularly showing this pattern, where clearing for agriculture creates brown squares and rectangles advancing into the deep green of intact rainforest. The land tells the story of human civilization, our capacity to reshape Earth's surface, and the consequences of our choices. Volcanic activity provides some of the most dramatic landforms visible from space. The volcanic arc of Indonesia stretches across thousands of kilometers, each volcano creating a distinctive cone shape. When eruptions occur, they're immediately visible from orbit, ash plumes rising into the stratosphere, creating dark gray or brown columns against white clouds or blue sky. These eruptions aren't just visually spectacular, They inject sulfur dioxide and other materials into the upper atmosphere, where they can spread globally and affect climate for years. The explosive 2022 eruption of Hunga Tonga. Hunga Ha'apai was clearly visible from space, creating a massive plume that reached the mesosphere and injected more water vapor into the stratosphere than any eruption since satellite monitoring began. From above, you watch these powerful geological processes that remind us Earth is still a dynamic, evolving planet. As we conclude our survey of continents and landforms, consider the diversity you've witnessed. From ice sheets to deserts, from rainforests to tundra, from mountain peaks to river deltas, Earth's land surfaces display an incredible range of environments, each supporting different forms of life, each shaped by different processes, each beautiful in its own way. This diversity isn't random. It's the result of precise factors including latitude, altitude, proximity to oceans, atmospheric circulation patterns, and geological history. The land you see from space represents billions of years of Earth history compressed into present-day geography, a landscape constantly being reshaped by wind, water, ice, volcanism, and increasingly by human activity. Understanding these landforms helps us understand our planet's past and anticipate its future in a time of unprecedented environmental change. From our orbital vantage point, weather systems reveal their true nature as massive, organized structures that span thousands of kilometers and operate according to precise physical laws. What appears chaotic from the ground, clouds forming and dissipating, winds shifting direction, rain falling unpredictably, from space shows clear patterns and structures. You can watch low-pressure systems organize themselves into characteristic spirals as the Coriolis effect causes air flowing toward low pressure to curve, creating those pinwheel shapes so familiar from weather maps. High-pressure systems create clear skies visible as vast blue or tan expanses free of clouds. Frontal boundaries appear as distinct lines of clouds where warm and cold air masses collide. Weather from space isn't chaos. It's a complex but comprehensible system operating according to thermodynamics, fluid dynamics, and Earth's rotation. Tropical cyclones, hurricanes, typhoons, and cyclones, depending on which ocean they form in, present perhaps the most spectacular weather phenomenon visible from space. A fully developed tropical cyclone shows unmistakable architecture, a clear, nearly cloud-free eye surrounded by towering eye-wall clouds that create a perfect circle with spiral rain bands extending outward like the arms of a galactic pinwheel. Hurricane Milton, photographed by ISS astronauts on October 8, 2024, displayed this classic structure as it achieved peak intensity of 180 mile-per-hour winds, becoming the most intense Gulf of Mexico hurricane on record. From above, you can see features invisible from the ground, overshooting cloud tops where convection is so intense it punches through the tropopause into the stratosphere. Above, anvil cirrus plumes spreading from the eyewall and gravity waves rippling through the upper atmosphere like rings spreading from a stone dropped in water. Satellites don't just provide pretty pictures, they're essential operational tools that save lives by tracking storms with precision impossible from the ground. The GOES R-series satellites, including GOES 19, which became operational as GOES East on April 7, 2025, provide images as frequently as every 30 seconds with 16-channel advanced baseline imager. This temporal resolution allows forecasters to watch storms intensify in near real time, to detect rapid intensification events that are particularly dangerous, and to track storm movements with accuracy measured in kilometers. The ISS orbit covers virtually all regions where tropical cyclones form, providing unique perspectives on storm structure. These observations aren't academic exercises. They directly inform evacuation decisions, emergency preparations, and warnings that protect millions of people in storm paths. Weather monitoring from space is literally a matter of life and death. Cloud formations visible from space display remarkable variety, each type revealing different atmospheric conditions and processes. Cumulus clouds appear as puffy white cotton balls scattered across blue sky. visual evidence of convection as warm air rises, cools, and condenses moisture. Stratocumulus creates rolling patterns like ocean waves formed by wind shear and stable atmospheric layers. Cirrus clouds, composed of ice crystals in the upper troposphere, create wispy, feather-like patterns that often predict weather changes days in advance. Marine stratocumulus clouds off the coast of California create vast fields of smooth white coverage that can extend for thousands of kilometers, reflecting enormous amounts of sunlight and playing a crucial role in Earth's energy balance. Each cloud type has meaning, tells a story about temperature, humidity, stability, and atmospheric dynamics happening at that location at that moment. Zeer weather produces distinctive signatures visible from space. Towering thunderstorm complexes appear as bright white clusters of clouds with overshooting tops, places where updrafts are so powerful they punch through the normal atmospheric boundary between troposphere and stratosphere. These storms can reach heights of 15 to 20 kilometers, creating anvil-shaped cloud tops that spread out when they hit the stable stratosphere. From orbit, you sometimes see above anvil cirrus plumes extending from these storms like smoke from a chimney. Tornado-producing supercells show characteristic features in satellite imagery, including bounded weak echo regions and hook echoes in radar data. Terekos, straight-line wind events, create bow-shaped arcs of clouds visible from hundreds of kilometers away. The atmosphere's violence becomes comprehensible when you can see the whole structure at once. Seasonal weather patterns create some of the most reliable yet beautiful phenomena visible from orbit. The intertropical convergence zone, where trade winds from northern and southern hemispheres meet near the equator, appears as a band of clouds that migrates north and south with the seasons, bringing rainy seasons to tropical regions. Monsoon systems create dramatic transformations. Trade wind clouds create repeating parallel bands across the Pacific that are so regular they look almost artificial. These patterns aren't random, they're the visible manifestation of Earth's energy balance, the planet's attempt to redistribute heat from equator toward poles, driven by solar heating and modulated by Earth's rotation and topography. Upper atmospheric phenomena add another layer of complexity to the weather systems we can observe from space. Atmospheric gravity waves appear as ripple patterns in clouds, created when air displaced by thunderstorms, hurricanes, terrain, or other disturbances generates oscillating motion that propagates both horizontally and vertically. Hurricane. Helene in October 2024 created gravity waves visible 55 miles up in the atmosphere, demonstrating how surface weather connects to the edge of space. Airglow, a faint emission distinct from auroras, appears as vibrant swaths of red, green, purple, and yellow light along Earth's limb, caused by atoms excited by daytime solar ultraviolet radiation releasing energy as photons. These phenomena reveal that our atmosphere isn't a passive envelope, but an active, dynamic system with complex internal interactions across multiple altitude ranges. As we complete our survey of weather systems, reflect on what you've witnessed. Every cloud you've seen, every storm system, every weather pattern represents energy in motion. Solar heat absorbed at the equator being redistributed toward poles, water evaporating from oceans and falling as rain on land, wind systems transporting moisture and momentum across thousands of kilometers. Weather isn't just something that happens to us. It's a fundamental expression of how Earth works as an integrated system. The atmosphere, oceans, land surfaces, ice sheets, and biosphere all interact to create the weather patterns we observe from space. Understanding these systems from an orbital perspective reveals the beauty in their complexity and the fragility in their balance. Climate change isn't just altering temperatures, it's modifying these fundamental atmospheric patterns with consequences we're only beginning to understand. One of the most profound experiences aboard the International Space Station is witnessing the boundary between day and night, what astronomers call the Terminator line. Every 45 minutes, we cross from daylight into darkness, or from darkness into light, experiencing 16 sunrises and 16 sunsets in each 24-hour period. This creates a rhythm entirely different from life on Earth's surface, a continuous cycle of illumination and shadow that reveals new aspects of our planet with each transition. As we approach the Terminator now, watch how the sun's angle creates long shadows that reveal terrain features invisible in overhead lighting. Mountains cast enormous shadows, clouds become three-dimensional sculptures, and the atmosphere itself becomes visible as layers of colored light. The Terminator isn't just a line on a map, it's a moving boundary between fundamentally different states of planetary existence. As we cross into night, Earth's character transforms completely. The familiar blues and greens and browns of daytime vanish, replaced by a dark canvas punctuated by points of light, cities, fishing fleets, gas flares, wildfires, and lightning. But before we lose the sun entirely, watch the atmosphere put on one of its most beautiful displays. The sunset from orbit happens in reverse. Instead of watching the sun sink below the horizon, we watch the shadow of Earth rise up toward us, extinguishing light layer by layer. The atmosphere creates a gradient of colors from brilliant yellow-orange where the sun still shines through, to deep reds and purples in the shadow zone, to the dark blue of night. This entire transition takes perhaps 3 to 4 minutes, compared to the leisurely half-hour sunsets you might experience from the ground. Time itself moves differently up here. The night side of Earth reveals patterns of human civilization invisible during daylight. Cities appear as brilliant clusters of light: New York, Tokyo, Sao Paulo, Cairo, their street grids creating geometric patterns of gold and white against the darkness. In the United States, the eastern seaboard appears as one continuous megalopolis of light from Boston to Washington, D.C. Europe glows from London to Moscow, the individual cities merging into fields of illumination. But it's not just cities. You can see highways as thin lines connecting bright nodes, see fishing fleets creating constellations of lights off Japan or Argentina, see gas flares from oil fields creating bright points in otherwise dark regions. This nighttime view reveals the extent and pattern of human presence on Earth in ways daylight photography cannot. We've literally made our mark on the night side of the planet. Natural phenomena also punctuate the night. Lightning appears as brief, bright flashes within clouds. Sometimes you can see entire thunderstorm complexes lighting up like flickering bulbs, each flash revealing the storm's internal structure for an instant. Wildfires create bright orange-red spots, sometimes with visible smoke plumes when illuminated by moonlight. Volcanic eruptions glow red with molten lava, creating eerie points of light in otherwise dark landscapes. The Aurora, which we'll explore in detail soon, creates vast curtains of green and red light flowing across high latitudes. Even bioluminescent plankton can occasionally be detected in long-exposure photographs as ghostly glows in the ocean. The night side isn't empty or inactive. It's simply revealing different phenomena, different stories about our planet's systems and processes. The Terminator line itself moves across Earth's surface at roughly 15 degrees of longitude per hour at the equator, about 1,700 kilometers per hour, the same speed at which the planet rotates. But from our orbital vantage point, moving in the same direction at much higher speed, we experience these transitions far more frequently. Think about that for a moment. On the ground, you experience one sunrise and one sunset per day. Up here on the ISS, we experience 16 of each. This rapid cycling creates its own biological challenges for astronauts. Circadian rhythms evolved over millions of years for 24-hour cycles don't adapt well to 90-minute days and nights. but it also provides unprecedented opportunities to study how light and shadow interact with Earth's features, how different phenomena appear under different illumination, how the planet functions both in light and in darkness. The transition from night back to day? The orbital sunrise offers its own wonders. First, you see a faint glow on the eastern horizon, the upper atmosphere catching sunlight before the surface does. This glow intensifies, progressing through a rainbow of colors as different atmospheric layers become illuminated. Then, suddenly, the sun appears as a brilliant point of light that quickly expands into a blazing arc, too bright to look at directly even through the station windows. The entire transition from darkness to full daylight takes only a few seconds. In that moment, Earth transforms from a dark sphere punctuated by human lights to a brilliant blue and white marble, clouds casting shadows, oceans reflecting light, the atmosphere glowing with its characteristic blue. Each sunrise brings renewed appreciation for this planet we call home. Moonlight adds another dimension to the nightside experience. When the moon is full or nearly full, it illuminates clouds, snow, and ice with a soft silver glow that makes these features visible even at night. Moonlit clouds over oceans create ethereal scenes of white forms floating above dark water. Snow-covered mountains and glaciers reflect moonlight brilliantly, appearing almost as bright as in daylight. The moon itself, rising or setting over Earth's limb, provides scale to the scene, a reminder that we're not just looking down at one planet, but observing multiple celestial bodies interacting. Moonlight photography from the ISS captures hauntingly beautiful images that seem almost otherworldly, yet they're just different lighting on the same Earth we see in daylight, demonstrating how much our perception depends on illumination. The dance of day and night, this eternal rotation that brings light and shadow in predictable cycles, is fundamental to life on Earth. Plants evolve to photosynthesize during daylight and respire at night. Animals adapted to be either diurnal or nocturnal, developing entire ecosystems around these light cycles. Human civilization organized itself around sunrise and sunset, despite our modern attempts to extend day with artificial light. From space, you see this cycle in its truest form, not as separate states, but as continuous transition, an endless flow from light to dark and back again. The Terminator line sweeping across the planet is more than a visual phenomenon. It's a reminder that Earth is a world in constant motion, rotating through space, forever turning toward and away from the sun that gives us life. Understanding this cycle from orbit provides perspective on our place within it. As we orbit through the night side of Earth, let's focus specifically on those clusters and networks of light that reveal human presence. From 400 kilometers up, city lights create maps of population density, economic activity, infrastructure development, and even cultural patterns. The brightest clusters correspond to megacities: Tokyo, New York, Cairo, Shanghai, where millions of people live and work in close proximity. But you can also see the highways connecting cities as thin golden threads, the smaller towns as scattered bright spots, the sprawl of suburbs creating halos around urban cores. This view reveals something profound. Humanity is not distributed evenly across Earth's surface. We cluster, we connect, we create networks that light up the night in patterns unique to our species. Different regions show different lighting patterns that reflect culture, economics, and development. The United States appears brilliantly lit coast to coast, with particularly dense illumination in the northeast corridor, around the Great Lakes, and along the west coast. Europe glows almost continuously from Britain through Russia, the interconnected cities creating a field of light interrupted only by seas, mountains, and forests. In contrast, much of Africa remains relatively dark, with Egypt's Nile River appearing as a bright ribbon through otherwise dark desert, and isolated bright spots marking cities like Lagos, Nairobi, and Johannesburg. These patterns aren't judgments of value, but they do reveal disparities in electrification, infrastructure, and economic development that have profound implications for human welfare and environmental impact. The night lights of Earth tell stories of who has access to resources and who doesn't. Some lights visible from space aren't cities at all. Fishing fleets, particularly those targeting squid off the coasts of Japan, Argentina, and Peru, create constellations of bright points that can number in the thousands. These boats use powerful lights to attract squid to the surface, and from orbit, entire fishing grounds appear to light up like floating cities in otherwise dark oceans. Gas flares from oil fields in the Middle East, North Dakota, and West Africa create isolated bright points in remote regions, each flare representing natural gas being burned off during petroleum extraction. These lights reveal economic activities invisible in daylight: extraction industries, commercial fishing operations, and resource exploitation happening in remote locations far from population centers. The nighttime view shows not just where people live, but where they work and what they do. The changing patterns of night lights over time tell stories of development, growth, and change. Astronauts who have flown multiple missions years apart report visible differences. Cities expanded into formerly dark areas, new highway networks connecting previously isolated regions, increased brightness in rapidly developing countries like China and India. Time-lapse compilations of nighttime imagery show cities pulsing with light as people wake up and go to sleep, factories operating in shifts, stadiums illuminating for events then going dark. During the COVID-19 pandemic, some areas showed measurably reduced nighttime lighting as lockdowns reduced economic activity and travel. The lights aren't static. They're dynamic indicators of human activity patterns, economic cycles, and societal changes happening in real time across the globe. Not all lights represent progress or prosperity. Wildfires create bright orange-red glows visible from space, sometimes with smoke plumes, visible when backlit by city lights or moonlight. In January 2025, multiple wildfires around Los Angeles created large, bright spots visible from orbit, forcing over 150,000 residents to evacuate. California's Park Fire in July 2024 became the state's fourth largest fire in history, burning 430,000 acres and producing smoke plumes reaching 5+ miles into the atmosphere. From space, these fires appear as ominous glows in the darkness, reminders of the increasing frequency and intensity of wildfires in a warming climate. The lights from fires tell different stories than the lights from cities, stories of disaster, destruction, and environmental change rather than human development and activity. The environmental implications of nighttime lighting are becoming increasingly recognized. Light pollution not only obscures our view of stars from the ground, but also affects ecosystems, disrupting bird migration patterns, confusing sea turtle hatchlings, altering predator-prey relationships for nocturnal animals, and affecting plant physiology. From space, you can see which regions prioritize dark sky preservation and which don't. Some cities have implemented shielded lighting that directs illumination downward rather than upward, reducing sky glow visible from orbit. Others continue to waste enormous amounts of energy lighting the sky unnecessarily. The nighttime view reveals humanity's attitude toward nature and conservation, whether we recognize our place within ecosystems or see ourselves as separate from them. How we light the night has consequences that extend far beyond simply enabling human activity after dark. Special events create unique lighting patterns visible from space. Major sporting events like the Olympics or World Cup light up stadiums in distinctive patterns. Holiday seasons bring increased illumination in countries that celebrate them, with decorative lighting adding to baseline infrastructure illumination. New Year's celebrations create bursts of light from fireworks that can be detected from orbit. Religious festivals like Diwali in India dramatically increase nighttime lighting across the entire subcontinent as millions light lamps and candles. These events remind us that the lights we see aren't just infrastructure. They represent culture, tradition, celebration, and the human need to gather and commemorate significant occasions. Even from 400 kilometers up, you can sense the rhythms of human life and society through these variations in nighttime illumination. As we prepare to leave the night side and cross back into day, consider what these lights mean. Each point of illumination represents people working, traveling, living their lives through the hours of darkness. The patterns reveal how we organize ourselves, where we choose to live, how we connect to each other, and how we use energy and resources. The brightness and extent of nighttime lighting has increased dramatically since the first nighttime photographs from space in the 1960s, reflecting population growth, urbanization, and development. But they also represent environmental impact, energy consumed, light pollution created, ecosystems disrupted. The lights of humanity are both beautiful and troubling, representing our achievements and our challenges. From space, you see both aspects simultaneously, the glory of human civilization and the burden it places on the planet that sustains us. Now we're approaching high latitudes as our orbit takes us toward the polar regions, and if conditions are right, if solar activity is strong and Earth's magnetic field is being buffeted by charged particles from the sun, we may witness one of the most spectacular phenomena visible from space, the aurora. From the ground, auroras appear as curtains of light dancing across the sky, green and sometimes red or purple, seeming almost magical in their movement and beauty. But from orbit, 400 kilometers up, we're actually inside the auroral zone, looking down at these lights from above. The perspective is completely different, revealing auroras not as distant phenomena, but as vast luminous structures wrapping around the poles like glowing crowns. What you're about to see will change how you think about the connection between Earth, Sun, and space itself. Let's understand what creates this phenomenon. The sun constantly emits a stream of charged particles, electrons and protons, called the solar wind, traveling through space at speeds up to 800 kilometers per second. When this wind reaches Earth, our planet's magnetic field deflects most of these particles around us, creating a protective cocoon called the magnetosphere. But at the poles, where magnetic field lines converge and dive into the atmosphere, some particles can follow these field lines downward, eventually colliding with atmospheric gases at altitudes between 80 and 500 kilometers. These collisions transfer energy to oxygen and nitrogen atoms, which then release that energy as light green from oxygen at 100 to 200 kilometers altitude, red from oxygen above 200 kilometers, and increasingly pink in recent observations. The aurora isn't just pretty lights, it's visible evidence of invisible space weather. The solar maximum reached in mid-2024 created some of the most spectacular auroral displays in decades, visible from unusually low latitudes, including central Mexico regions that typically never see auroras at all. From the ISS, astronauts described constantly transforming curtains of light, sometimes red, sometimes green, often both simultaneously in layered structures. ESA astronaut Thomas Pesquet wrote during his mission, "The view at night recently has been simply magnificent. Few clouds, intense auroras. I can't look away from the windows." That statement captures something essential about auroras. They're hypnotic, mesmerizing in ways that static features like mountains or oceans aren't. The constant movement, the flowing patterns, the shifting colors create a sense of the atmosphere as a living, breathing entity responding to forces beyond Earth itself. Colors in auroras aren't random. They tell specific stories about atmospheric composition, altitude, and energy levels. The most common color, that characteristic emerald green, comes from oxygen atoms at roughly 100 to 200 kilometers altitude. These atoms get excited by particle collisions, then after a brief delay emit green light at 558 nanometers wavelength. Higher altitude oxygen creates red auroras, visible at 200 to 400 kilometers, where the atmosphere is thinner and atoms have more time between collisions. Nitrogen creates blue and purple colors, though these are less common and usually appear at lower edges of auroral displays. Recently, increased pink coloration in auroras has been observed, particularly during intense geomagnetic storms. From orbit, you can see these colors layered vertically, creating rainbows of light that extend from near space down toward the denser atmosphere below. Auroral forms visible from space include distinct types that researchers have classified and studied. Curtain auroras appear as vertical sheets of light, often with clear folds and waves like drapery hanging in the atmosphere. Arc auroras create smooth, bow-shaped structures extending east-west across the polar sky. Corona auroras show rays that appear to radiate from a central point directly overhead when viewed from the ground, but from space reveal themselves as parallel structures aligned with magnetic field lines converging toward the magnetic pole. During intense geomagnetic storms, discrete auroral structures can break down into more diffuse glows covering vast areas, or into rapidly moving forms called auroral substorms where energy releases cause sudden brightenings and expansions. Each form reflects different magnetospheric conditions, different energy input levels, different states of the space environment surrounding Earth. Airglow, often confused with aurora, is actually a distinctly different phenomenon visible from the ISS. Unlike auroras energized by solar wind particles, airglow results from ordinary chemical reactions and recombination processes in the thermosphere. During daytime, solar ultraviolet radiation excites atoms and molecules. After sunset, those excited species gradually release stored energy as photons, creating a faint emission that appears as vibrant swaths of red, green, purple, and yellow light along Earth's limb. Airglow is always present, not dependent on solar activity like auroras. It's brightest at 85 to 95 kilometers altitude, creating a distinct layer visible in ISS photography. Scientists use airglow to study upper atmospheric temperature, density, and composition, tracking atmospheric gravity waves and other phenomena. From orbit, airglow and aurora often appear simultaneously at different altitudes, creating layered light structures of extraordinary complexity and beauty. The aurora australis, southern lights, mirrors the aurora borealis in the northern hemisphere, though it's less frequently observed simply because the southern polar region contains mostly ocean and Antarctic ice with very few human observers. From orbit, we see both auroral zones in each orbit period, providing unique opportunities for comparison and study. Recent ISS photography has captured magnificent views of the aurora australis over Antarctica and the Southern Ocean, revealing that these southern displays can be just as spectacular as their northern counterparts. During strong geomagnetic storms, both auroral ovals expand toward the equator simultaneously, creating a global auroral response to space weather events. The symmetry isn't perfect. Earth's magnetic field is slightly offset from the geographic poles and isn't perfectly dipolar. But the basic pattern holds. Our planet wears two auroral crowns, one at each pole, responding in concert to the variable solar wind. What makes auroras particularly special from the ISS perspective is that astronauts can watch them evolve in real time, see them respond to changes in solar wind conditions, observe the moment when a substorm begins and auroral forms suddenly brighten and expand. They report that no two auroral displays are exactly alike, each one unique in color, form, intensity, and behavior. The aurora reminds us that Earth isn't isolated in space but constantly interacting with its stellar environment, that our magnetic field and atmosphere work together to protect us from particle radiation that would otherwise strip away our protective envelope. The dancing lights are beautiful, yes, but they're also functional, evidence of protection systems that make life on Earth's surface possible. As we watch these lights flow and shift, we're witnessing the dynamic interaction between star and planet, between solar wind and terrestrial magnetic field, between space environment and atmospheric response. The aurora is where Earth and space meet in a visible, beautiful, scientifically rich phenomenon. We've seen Earth's beauty, its systems, its phenomena. but we must also acknowledge what satellite observations reveal about changes happening to our planet. 2024 was confirmed as the warmest year in instrumental records by multiple independent agencies including NASA, NOAA, Copernicus, and the World Meteorological Organization. Global temperature reached 1.6 degrees Celsius above pre-industrial levels, with July 22nd setting the record for Earth's hottest day ever measured at 17.16 degrees Celsius mean temperature. These aren't abstract statistics, they're measurable realities, visible from space through melting ice, changing vegetation patterns, more intense storms, and shifting climate zones. The view from orbit that has inspired so much awe and wonder also reveals a planet under stress from human activities. Understanding these changes isn't pessimism, it's necessary realism that can motivate action. Polar ice provides the most dramatic visible evidence of climate change from orbit. Antarctic sea ice hit its second lowest winter maximum in satellite history on September 19, 2024, at 17.16 million square kilometers, just 200,000 square kilometers above 2023's record low and 1.55 million square kilometers below the long-term average. The summer minimum on March 1, 2025, tied for second lowest at 1.98 million square kilometers, 30% below the long-term average. The 5 lowest summer minimums have all occurred since 2017, suggesting a potential regime shift. Arctic sea ice continues declining at 12.4% per decade, with the last 18 years representing the 18 lowest extents in the 45-year satellite record. From space, you can watch this ice retreat year after year, the white cap shrinking as dark ocean water absorbs more sunlight, creating a feedback loop that accelerates warming. Greenland's ice sheet, visible from orbit as a vast white dome covering an area roughly the size of Alaska, is losing mass at accelerating rates. Satellite gravity measurements detect ice loss even when visual changes aren't obvious, revealing that Greenland shed approximately 280 billion tons of ice per year on average during the past 2 decades. From space, you can see meltwater rivers forming on the ice surface during summer, draining into moulins, vertical shafts that carry water to the bedrock below, where it can lubricate ice flow and accelerate glacier movement toward the ocean. The edges of the ice sheet show glaciers calving massive icebergs into the sea, events sometimes visible in satellite imagery as new sections of blue water appearing where ice recently existed. These changes aren't projections or models, they're observable, documented processes happening right now, visible from our orbital vantage point. Vegetation patterns tracked by satellite reveal climate zones shifting poleward as temperatures rise. The greening of the Arctic, where shrubs and trees expand into areas previously too cold to support them, is clearly visible in multi-year comparisons of satellite imagery. The Amazon rainforest, that deep green expanse we saw earlier, shows concerning trends: reduced dry season greenness in some areas, increased fire frequency, and brown patches of deforestation expanding into intact forest. During 2024, atmospheric carbon dioxide jumped by 3.75 parts per million, the largest single-year increase ever recorded, bringing levels to 424 parts per million, 50% above pre-industrial concentrations. Projections suggest May 2025 will hit 429.6 parts per million. The Amazon, which normally acts as a carbon sink absorbing CO2, shows signs of stress that could reduce or reverse this function, turning a climate buffer into a climate accelerator. Ocean heat content reached record levels in 2024, with the upper 2,000 meters of ocean containing more thermal energy than ever measured. The increase from 2023 to 2024 equaled 140 times the world's total electricity generation. This heat doesn't just sit there. It intensifies tropical cyclones like the ones we observed earlier, provides energy for more extreme precipitation events, and contributes to sea level rise through thermal expansion. Ocean color satellites detect changes in phytoplankton blooms and ocean productivity, revealing shifts in marine ecosystems responding to warming waters. Coral bleaching events, visible from space as reefs changing from vibrant colors to pale white, have become more frequent and severe. The oceans that cover 71% of our planet are absorbing 90% of the excess heat from greenhouse gas warming, buffering atmospheric temperature increases, but paying a biological price that threatens marine ecosystems worldwide. Extreme weather events captured by satellites demonstrate the increasing intensity of storms, fires, floods, and droughts in a warming world. Hurricane. Helene made landfall on September 26, 2024, as a Category 4 storm, dumping up to 30 inches of rain and claiming at least 230 lives. Just 13 days later, Hurricane Milton struck after achieving peak intensity of 180 mile-per-hour winds. California's Park Fire in July 2024 burned 430,000 acres. In January 2025, multiple wildfires erupted around Los Angeles. From orbit, these events appear with stark clarity. Massive storm systems, vast smoke plumes, flooded regions visible as expanded water coverage. The frequency and intensity aren't just subjective impressions. They're statistically documented trends that correlate with rising global temperatures. The atmosphere, holding 7% more moisture for each degree Celsius of warming, delivers that moisture in more intense precipitation events or withholds it in more severe droughts. Yet viewing these changes from space also reveals reason for hope and potential for solutions. Solar panel installations appear as blue-black geometric patterns in desert regions. Massive solar farms in California's Mojave Desert, China's Gobi Desert, or Australia's Outback, capturing sunlight to generate clean electricity. Wind farms create distinctive patterns of regularly spaced turbines visible in satellite imagery. Reforestation projects show as expanding green areas in regions previously degraded. The same satellite systems documenting problems also track solutions, monitor compliance with environmental agreements, verify carbon sequestration projects, and provide data for climate models that help us understand future scenarios. From orbit, you can see both the damage and the healing, both the challenges and the responses. The view doesn't dictate despair or optimism, but rather provides information. What we do with that information determines outcomes. The perspective from space makes one thing undeniable: Earth is a closed system. There's nowhere for pollution to go but into our air, water, or soil. There's no external source of additional resources. The thin blue line of atmosphere we observed earlier contains all the air we'll ever have. The water cycling through oceans, clouds, and rivers is the same water that's always been here. Changes we make aren't happening somewhere else or to someone else. They're happening here, to our only home, to the planet that sustains us. This realization, visceral and undeniable from orbit, is perhaps the most important insight the space age has provided. Not technological capabilities, not scientific discoveries, but perspective. Seeing Earth whole, understanding it as a system, recognizing our place within rather than above it. The overview effect isn't just psychological, it's practical, providing the perspective necessary to make wise choices about our shared future. There's a phenomenon that occurs when humans see Earth from space, something so consistent across cultures, nationalities, and backgrounds that researchers have studied it formally and given it a name: the overview effect. Frank White coined this term in 1987 after interviewing over 30 astronauts about their experiences. He defined it as a cognitive shift characterized as a state of awe with self-transcendent qualities precipitated by a particularly striking visual stimulus. In simpler terms, seeing Earth from space fundamentally changes how you think about yourself, humanity, and our place in the universe. This isn't poetic exaggeration or spaceflight romanticism. It's a documented psychological phenomenon with measurable effects on attitudes, values, and behaviors. Let's explore what this experience means and why it matters for all of us, even those who will never leave Earth's surface. Astronaut testimonies reveal remarkable consistency despite diverse cultural backgrounds and personal beliefs. Edgar Mitchell of Apollo 14 described an explosion of awareness and overwhelming sense of oneness and connectedness, accompanied by an ecstasy. He added, I had a feeling it's tiny, it's shiny, it's beautiful, it's home, and it's fragile. More recently, Ed Dwight, who flew on Blue Origin at age 90 in 2024, looked out the window and said, "Everything looked ordered and neat and wonderful and beautiful. There was no separation between countries or states." And you ask yourself, as wonderful as it all is, why can't the people who live on it get along? The experience transcends intellectual knowledge. NASA astronaut Don Lind explained, "Intellectually, I knew what to expect. I have probably looked at as many pictures from space as anybody, so I knew exactly what I was going to see. But there is no way you can be prepared for the emotional impact." This distinction is crucial. Many people know facts about Earth, its size, composition, appearance from space. We've seen countless photographs. But the overview effect isn't about information, it's about direct experience that bypasses intellectual filters and strikes at something deeper. Seeing Earth with your own eyes from space creates an understanding that photographs alone cannot convey, a visceral comprehension of planetary fragility and unity that fundamentally alters perception. This suggests that the perspective itself, not just the information it provides, carries transformative power. Psychological research has identified three primary components of the overview effect. First, awe, arising from perceiving both perceptual vastness, the planet's physical scale, and conceptual vastness, humanity's interconnectedness and our place in the cosmos. Second, self-transcendence, where individual concerns temporarily diminish as you realize you're part of something vastly larger than yourself, connected to all life on Earth. Third, cognitive schema changes requiring expansion of your conceptual framework to incorporate perspectives that challenge existing worldviews. This isn't merely emotional, it's fundamentally cognitive, requiring mental models to expand and adapt to accommodate the new perspective. The experience often includes reduced self-salience, increased feelings of connectedness, and heightened environmental concern. These aren't temporary mood changes, but lasting alterations in how people understand themselves and their relationship to Earth and humanity. The view from space makes borders disappear in the most literal sense. From orbit, you see no lines dividing nations, no walls separating peoples, no markers indicating where one country ends and another begins. The geopolitical divisions that dominate news cycles, drive conflicts, and organize human society simply don't exist from 400 kilometers up. You see natural features, continents, oceans, rivers, mountains, and sometimes human features like cities or agricultural patterns, but nothing indicating political boundaries. This visible erasure of borders creates a powerful realization. These divisions are human constructs, not fundamental realities. The atmosphere you're breathing doesn't stop at national borders. The ocean currents don't recognize territorial waters. The climate system doesn't care about geopolitics. We've created boundaries that the planet itself doesn't acknowledge, and seeing this from space makes the arbitrary nature of these divisions undeniable. Scientific studies confirm the overview effect produces measurable changes in attitudes and behaviors. Research shows moderate increases in perceptions of Earth as a beautiful, fragile object to be treasured significantly correlate with subsequent involvement in environmental causes and pro-social behaviors. Virtual reality research offers hope for democratizing this experience. A 2024 study with 60 participants using immersive VR showed significant increases in nature relatedness scores in the experimental group, suggesting technology may eventually make aspects of the overview effect accessible beyond the elite astronaut corps. This matters because the perspective shift could be exactly what humanity needs to address global challenges requiring cooperation, long-term thinking, and recognition of our shared fate. If seeing Earth from space changes how individuals think about the planet, Perhaps enabling more people to access this perspective could catalyze collective action at the scale necessary to address climate change, biodiversity loss, and other planetary scale challenges. Carl Sagan synthesized the cosmic perspective for all of us in his reflection on the pale blue dot photograph. When Voyager 1 turned its camera around from 6.4 billion kilometers away on February 14, 1990, Earth appeared as a crescent only 0.12 pixel in size, caught in scattered sunlight. Sagan wrote, "Look again at that dot. That's here. What's home? That's us." Force task to spend in the sun beetle one the sasan tantandasa handawas. As we complete this exploration of the overview effect, consider what it means for you personally. You may never physically travel to space, but you've now seen Earth from that perspective through these images and descriptions. You've watched our planet rotate beneath us, observed its systems in action, witnessed both its beauty and its fragility. Does this change anything for you? Do borders seem less important? Does the atmosphere seem more precious? Do human conflicts appear smaller against the backdrop of cosmic scale? The overview effect isn't reserved exclusively for astronauts. It's a perspective that anyone can cultivate, a way of seeing Earth that recognizes its uniqueness, its fragility, and our shared responsibility for its care. Perhaps the most important legacy of the space age isn't the technology or the scientific discoveries, but this simple yet profound shift in perspective that comes from finally seeing our home as it truly is: one planet, one humanity, one shared fate among the stars. Throughout our journey, we've looked at individual features: oceans, continents, atmosphere, weather, ice, lights. But now let's step back and see how everything connects. Earth isn't a collection of separate systems operating independently. It's a single integrated whole where changes in one system cascade through all others. The water evaporating from oceans becomes the clouds that bring rain to forests. Those forests absorb carbon dioxide and release oxygen that travels globally through atmospheric circulation. Rivers carry nutrients from mountains to oceans, feeding phytoplankton that form the base of marine food webs. Every system touches every other system in feedback loops, both stabilizing and amplifying. This interconnectedness, invisible when you're on the ground focused on local phenomena, becomes undeniable from orbit where you can see the whole planet functioning as one entity. The water cycle provides perhaps the clearest example of planetary interconnection visible from space. Watch water evaporate from warm tropical oceans, invisible to our eyes but measurable by satellites through humidity sensors. That moisture rises into the atmosphere where it forms clouds, white structures we can see from orbit. Atmospheric circulation, driven by solar heating and Earth's rotation, transports those clouds thousands of kilometers, sometimes in narrow bands called atmospheric rivers carrying water equivalent to multiple Mississippi rivers. The clouds eventually release their moisture as rain or snow, falling on continents where it flows through rivers back to the ocean, completing the cycle. But this isn't just water moving. It's energy transport, climate regulation, nutrient distribution, and the foundation of terrestrial life. The water you drank this morning has cycled through this system countless times over billions of years, connecting you physically to ancient oceans, prehistoric rain, and future clouds. The carbon cycle connects atmosphere, ocean, land, and life in an intricate web of exchanges. Terrestrial photosynthesis draws 120 gigatons of carbon annually from atmosphere to plants. You can watch this happen from space as continents green during growing seasons. Plant and soil respiration returns roughly the same amount, creating the breathing cycle we observed earlier. Oceans exchange 90 gigatons in each direction through gas dissolution and biological activity. The ocean color changes we've seen. Phytoplankton blooms, varying water tints, represent biological carbon pumps moving carbon from surface waters to deep ocean storage. Volcanic activity releases carbon from Earth's interior. Rock weathering slowly removes atmospheric carbon over geological timescales. Human activities inject additional carbon through fossil fuel combustion and land use changes, visible from orbit as industrial regions, cities, deforestation patches, and agricultural expansion. The carbon atom in your body right now has cycled through this system many times. Perhaps it was once in a dinosaur, or ocean plankton, or a volcanic gas, or an ancient forest. Ocean currents and atmospheric circulation work together to redistribute heat from equator toward poles, moderating planetary temperatures and making vast regions habitable. The Gulf Stream we observed earlier carries warm water northward, where heat releases into the atmosphere, warming European weather. That water, cooled and made saltier by evaporation, eventually sinks in the North Atlantic, forming deep currents that flow southward and eventually connect to the global conveyor belt circulation linking all ocean basins. Atmospheric circulation patterns like the Hadley cell, Ferrel cell, and polar cell transport heat vertically and horizontally, creating the climate zones and wind patterns we observe from orbit. These coupled ocean-atmosphere systems operate continuously, adjusting to changes in solar input, ice coverage, and atmospheric composition. From space, you can sometimes see visual evidence of these connections. Warm ocean currents creating fog or clouds, cold currents creating clear zones, convergence regions where different air masses meet and produce weather systems. The biosphere. All life on Earth actively participates in regulating planetary conditions through processes collectively called Gaia theory or Earth system science. Forests don't just exist within climate conditions, they modify them, releasing moisture that becomes rain, absorbing sunlight that would otherwise heat the surface, drawing down carbon that affects global temperatures. Phytoplankton in oceans don't just respond to ocean conditions, they influence them, producing dimethyl sulfide that affects cloud formation, altering ocean pH through photosynthesis, and sequestering carbon to ocean depths when they die and sink. Wetlands store carbon, purify water, and moderate flood cycles. Coral reefs protect coastlines while building structures from dissolved minerals. Life isn't passive in Earth systems. It's an active agent that helps maintain the conditions necessary for its own survival. This recognition transforms how we think about environmental protection. We're not just preserving pretty scenery or charismatic species, but protecting functional components of planetary systems that regulate habitability. Feedback loops, both positive and negative, regulate Earth's systems and determine how the planet responds to changes. We've seen the ice albedo feedback. Melting ice exposes darker surfaces that absorb more heat, causing more melting. The water vapor feedback operates similarly. Warming air holds more moisture, and since water vapor is a greenhouse gas, it amplifies initial warming. These are positive feedbacks. They amplify changes. But negative feedbacks provide stability. As Earth warms, infrared radiation to space increases, providing thermodynamic limits on runaway warming. Weathering of rocks removes atmospheric carbon dioxide over geological time. Cloud feedbacks can be either positive or negative depending on cloud type and altitude. From orbit, you can't directly see these feedbacks operating, but you can observe their consequences. Ice sheets changing size, vegetation zones shifting, storm intensities varying, atmospheric composition altering. Understanding these feedbacks helps predict how Earth will respond to continued human pressures and how we might work with natural systems rather than against them. Satellite observations have revolutionized our understanding of these interconnected systems by providing global, continuous, and consistent measurements impossible from ground stations alone. The fleet of Earth observation satellites operates 24 hours per day, monitoring everything from sea surface temperatures to atmospheric carbon dioxide concentrations to vegetation health to ice sheet thickness. These measurements feed into Earth system models that attempt to capture the complexity of interconnections and feedbacks. When models predict futures under different scenarios, they're not crystal ball gazing, but rather mathematical representations of physical processes informed by satellite observations. The better our observations from space, the better we understand current conditions and connections, and the more accurately we can project futures. This knowledge isn't academic. It informs policy decisions, agricultural planning, water resource management, disaster preparedness, and climate mitigation strategies affecting billions of people. As we conclude this exploration of Earth's interconnected systems, reflect on a profound implication. Changing one system inevitably affects others in ways both predictable and surprising. Altering atmospheric composition changes climate, which affects ice sheets, which influences ocean currents, which modifies weather patterns, which impacts vegetation, which alters carbon cycling, which feeds back to atmospheric composition. There's no way to change just one thing. Everything connects to everything else. This interconnectedness makes Earth both resilient, able to absorb and adapt to disturbances through system adjustments, and vulnerable, capable of crossing tipping points where feedback loops cause rapid, potentially irreversible changes. From orbit, you see this interconnection as obvious, visible, undeniable. Systems that seem separate from ground level reveal their connections when viewed from space. This perspective suggests that addressing environmental challenges requires systems thinking, recognizing that solutions must account for connections, feedbacks, and cascading effects throughout the integrated whole we call Earth. We're completing our final orbit now, having traveled around Earth together, witnessing its beauty, understanding its systems, observing its changes, and experiencing something of the perspective shift that comes from seeing our planet from space. Soon, it will be time to return to the surface, to go back to daily life on the ground where the cosmic perspective fades and local concerns dominate attention. But perhaps something of what you've seen and understood will remain with you, influencing how you think about Earth and your place upon it. This transition from the orbital perspective back to ground level mirrors the experience astronauts describe when returning from space. They've seen something that changes them permanently, yet they must reintegrate into a world that hasn't shared that direct experience. Their challenge, and perhaps ours after this journey together, is carrying the perspective forward, allowing it to inform choices and actions in daily life. What does it mean to carry the orbital perspective into daily life? It might mean recognizing that the air you breathe connects you physically to every other breathing organism on the planet, circulating globally and mixing completely in roughly 1 year. The water you drink has cycled through clouds, oceans, rivers, and bodies for billions of years, connecting you chemically to ancient seas and future rains. The atoms in your body were forged in stellar interiors and distributed through space by supernova explosions, making you literally star-stuck contemplating the cosmos. These aren't poetic metaphors, but physical realities. The orbital perspective makes abstract knowledge visceral. You are not separate from Earth or from other humans, but connected through multiple physical, chemical, and biological systems. This recognition, truly internalized, changes how you see yourself and your relationship to the world around you. Responsibility emerges naturally from understanding and connection. When you see Earth as finite, fragile, and beautiful from space, when you recognize that we truly share one planet with no backup option, when you understand that systems are interconnected and human actions have planetary consequences, then questions of responsibility become unavoidable. What are we responsible for? To whom or what? How should that responsibility influence choices and actions? These aren't questions with single answers, but they're questions worth asking. The astronauts who have seen Earth from space often report feeling an increased sense of responsibility to protect the planet, to advocate for environmental stewardship, to work toward human cooperation on shared challenges. Perhaps this responsibility flows from love. Seeing Earth's beauty from space makes you want to protect it. Perhaps it flows from fear. Seeing Earth's fragility from space makes you want to prevent damage. Most likely, it flows from both. Individual actions matter within complex systems, even when any single action seems insignificant against planetary scale. The choices you make about energy use, consumption, transportation, diet, and lifestyle aggregate with billions of others to create the collective patterns visible from orbit. Patterns of resource use, land transformation, atmospheric composition change, and ecosystem modification. From space, individual humans are invisible, but human impacts are obvious. This paradox, individuals invisible but impacts visible, suggests that solutions require both personal responsibility and collective action, individual choices and systemic changes, local efforts and global cooperation. The orbital perspective doesn't provide specific policy prescriptions or tell you exactly what to do, but it does suggest that the stakes are high, the challenges are real, and the responses must match the scale of planetary-level problems with planetary-level thinking. Hope exists alongside concern when viewing Earth from space. Yes, the planet faces unprecedented challenges from human activities. Yes, climate change, biodiversity loss, ocean acidification, and resource depletion threaten ecosystems and human well-being. But you've also seen Earth's resilience, its systems' capacity to absorb disturbances and adapt to changes, its 4 billion years of surviving cosmic impacts, volcanic eruptions, ice ages, and mass extinctions. You've seen evidence of human ingenuity. Solar farms, wind turbines, reforestation projects, and protected areas visible from orbit. You've recognized that the same species capable of causing planetary-scale damage is also capable of planetary-scale solutions. The question isn't whether Earth will survive. It will, in some form. The question is whether Earth will remain habitable for human civilization and the current biosphere we've evolved alongside. That outcome isn't predetermined. It depends on choices we make collectively in coming years and decades. Education and perspective sharing might be among the most important tools we have for addressing planetary challenges. If seeing Earth from space changes how people think about the planet and their responsibilities toward it, then making that perspective accessible through imagery, virtual reality, education, storytelling, and experiences like this documentary becomes critical. You can't send everyone to space, but you can show them what astronauts see and share what astronauts feel. Research suggests even virtual experiences of the overview effect can shift environmental attitudes and increase prosocial behaviors. This implies that the work of space agencies, educators, documentary filmmakers, and science communicators isn't peripheral to solving environmental challenges, but central to developing the collective consciousness and will necessary for planetary stewardship. The more people who see Earth from the cosmic perspective, the more people who might carry that perspective into decisions, actions, and advocacy. Carl Sagan wrote that our obligation to survive is owed not just to ourselves, but also to that cosmos, ancient and vast, from which we spring. This perspective places Earth and humanity within the largest possible context. We're not just protecting environment for human benefit. We're protecting the only known instance of life and consciousness in the universe, the outcome of billions of years of cosmic and biological evolution, the universe's way of knowing itself. From the cosmic perspective, Earth isn't just our home, it's precious beyond measure as the only place we know where matter has organized itself into living systems capable of understanding and appreciating the cosmos from which they came. Whether or not other life exists elsewhere in the universe, and we don't yet know, Earth represents something extraordinary, worth protecting. The orbital perspective provides not just environmental motivation, but existential meaning, connecting daily choices to cosmic significance. As our journey concludes and we prepare to return to Earth's surface, take one last look at this magnificent planet spinning beneath us. Notice the blue of the oceans, the white of the clouds, the thin line of atmosphere protecting everything we've ever known. Feel the sense of connection to those billions of people down there, all sharing this one home, all breathing the same air, all depending on the same planetary systems. Remember that borders are invisible from here, that the whole planet operates as one integrated system, that what affects one part eventually affects all parts. Carry this perspective with you as you return to daily life. Let it inform how you see yourself, how you relate to others, how you think about the future. The orbital view isn't just for astronauts, it's for everyone, a way of seeing that can transform how we live on and care for the only home we've ever known. Thank you for joining me on this journey. May the perspective stay with you always. Our hour-long tour of Earth from space has come to an end, but the journey of understanding and protecting our planet continues every day. The view from 400 kilometers up has shown us what astronauts have known for decades. Earth is beautiful beyond words, fragile beyond measure, and precious beyond value. It's the only home we have, the only place in the vast universe where we know life exists. As you return to your life on the surface, perhaps you'll carry something of this orbital perspective with you. Perhaps when you look up at the sky, you'll remember seeing it from above. Perhaps when you hear about distant countries, you'll remember seeing them all at once from space with no borders dividing them. Perhaps when you think about environmental challenges, you'll remember how thin that protective atmosphere really is. If this journey has touched you, if it's changed even slightly how you see Earth and your place upon it, then consider sharing that perspective with others. We're all crew members on this spaceship, Earth, and understanding our shared home is the first step toward caring for it together. Until we meet again, may you find peace in the cosmos and purpose in protecting our pale blue dot.